This is part 1 of lecture 1.1 of Math 23, Functions of Several Variables. In this video, we will give the definition of a real-valued function of two or more real variables, and we will learn how to find the domain of such a function. We begin by recalling the following concepts. Let n be an integer that is greater than or equal to 2. An ordered n-tuple is a set of n objects, not necessarily distinct, having a particular arrangement. Note that an ordered n-tuple is determined both by the objects in the n-tuple together with the way that the objects are arranged. Hence, two ordered n-tuples A1, A2 up to AN and B1, B2 up to Bn are equal exactly when AI and Bi are equal for all indices I from 1 to n. In particular, the set of all ordered n-tuples of real numbers is denoted by Rn. We sometimes refer to the elements of Rn as points. You learned in your previous math courses that R2 can be represented visually using the two-dimensional Cartesian coordinate system, also known as the Cartesian plane. This coordinate system consists of two number lines, called the axes, drawn in the plane perpendicular to each other and meeting at their origins. Usually, one axis is horizontal and the other is vertical. Given a point in the plane, we draw perpendiculars from the point to each of the axes. The point has coordinates AB, where A is the coordinate of the foot of the perpendicular to the horizontal axis, and B is the coordinate of the foot of the perpendicular to the vertical axis. The graph of a subset D of R2 consists of all points in the Cartesian plane whose coordinates belong in D. Likewise, R3 can be represented visually using the three-dimensional Cartesian coordinate system. This coordinate system consists of three number lines, called the axes, which are mutually perpendicular and meet at their origins. These are usually called the X, Y, and Z axes, and their orientation relative to each other follows the so-called right-hand rule. Given a point in space, we draw perpendiculars from the point to each of the axes. The point has coordinates A, B, C, where A is the coordinate of the foot of the perpendicular to the x-axis, B is the coordinate of the foot of the perpendicular to the y-axis, and C is the coordinate of the foot of the perpendicular to the z-axis. The graph of a subset D of R3 consists of all points in space whose Cartesian coordinates belong in D. There is no analogous visual representation for Rn for n greater than 3. We now recall the definition of a function. Let x and y be sets. A function f from x to y is a rule or correspondence that associates to every element small x in the set capital X exactly one element small y in the set capital Y. Note that under this correspondence, different elements in the set X may correspond to different elements in the set Y. Also, an element in the set Y may correspond to more than one element in the set X. The domain of the function f is the set capital X of all input values, while the range of f is the set of all output values. That is, the range consists of all elements f of small x in the set Y, as small x varies over all elements in the set capital X. Note that the range of f is a subset of Y and is sometimes, but not always, equal to Y. We use the following notation to denote f, the domain of f, and the range of f. In the special case where the set Y is a subset of the set of real numbers, we say that f is a real-valued function. And if x is a subset of the set of all ordered n-tuples of real numbers, then f is a function of n real variables. Thus, a real-valued function of n real variables is a function from a subset x of Rn to a subset y of R. The following is the common notation used to denote a real-valued function of 1, 2, 3, or more variables. In Math 21 and 22, you studied the calculus of real-valued functions of one real variable. In particular, you learned about limits, derivatives, and integrals of real-valued functions of one variable. Here in Math 23, we will study the calculus of real-valued functions of 2, 3, or n real variables for n greater than 1. We will extend the concept of limits, derivatives, and integrals from the single variable case to the multivariable case. For the rest of the course, until the study of the calculus of vector fields, all functions discussed are assumed to be real-valued and of n real variables. Let us now look further at the domain and range of a function of n variables. Let f be a function from x to y, where x is a subset of Rn and y is a subset of R. As we said previously, x is the domain of f. However, there are instances in which x is not specified. For example, when we are given only an equation y equals f of x1, x2, up to xn. In this case, we define the domain of f to be the set of all points in Rn for which the expression f of x1, x2, up to xn is a real number. In general, it is more difficult to find the range of a function than it is to find its domain. In some special cases, for instance, when the graph of the function is a known surface, it is possible to deduce the range of f. We will focus only on finding the domain of a function in this course. Let us look at some examples. Consider the function f of two variables defined by the equation f of xy equals 1 over the square root of x squared minus y. The domain of f is not specified, so following our convention, we define the domain of f to be the set of all points x, y in R2 for which 1 over the square root of x squared minus y is a real number. This is precisely the set of all points x, y for which the square root of x squared minus y is a non-zero real number, which in turn is the set of all points x, y for which x squared minus y is a positive real number. Rewriting, we get the domain of f to be the set of all points x, y satisfying the inequality y is less than x squared. The graph of this set in the Cartesian plane is the set of all points below the parabola y equals x squared, excluding all points on the parabola itself. Now consider the function g with g of xyz given by the natural logarithm of 1 minus x squared minus y squared minus z squared. Again, the domain of g is not specified. So under our convention, the domain of g consists of all points x, y, z for which the natural logarithm of 1 minus x squared minus y squared minus z squared is a real number. This is precisely the set of all points x, y, z for which 1 minus x squared minus y squared minus z squared is greater than 0, which in turn is the set of all points x, y, z satisfying the inequality x squared plus y squared plus z squared is less than 1. The graph of this set in R3 consists of all points enclosed by the unit sphere, excluding all points on the unit sphere itself. As a final remark, we note that not all equations which involve the variables x1, x2, up to xn, and y define y as a function of x1, x2, up to xn. Such an equation defines y as a function of the other variables exactly when the following condition holds. For each n-tuple x1, x2, up to xn in Rn, there is at most one real number y, such that the n plus 1 tuple x1, x2, up to xn, y satisfies the equation. For example, the equation xy equals 1 defines y as a function of x, since for each non-zero real number x, there is a unique real number y, namely 1 over x, such that the ordered pair xy satisfies the equation. On the other hand, the equation x squared plus y squared equals 1 does not define y as a function of x, since for certain values of x, we can find more than one value of y such that the ordered pair xy satisfies the equation. In particular, the ordered pairs 0, 1 and 0 minus 1 both satisfy the equation, so x equals 0 corresponds to two different values of y. The equation x plus y plus z equals 1 defines z as a function of x and y, since for each ordered pair xy of real numbers, there is a unique real number z, namely 1 minus x minus y, such that the ordered triple x, y, z satisfies the equation. The equation x squared plus y squared plus z squared equals 1 does not define z as a function of x and y, since for certain ordered pairs xy, we can find more than one value of z such that the ordered triple xyz satisfies the equation. In particular, the ordered triples 0, 0, 1 and 0, 0, minus 1 both satisfy the equation. So the ordered pair 0, 0 corresponds to two different values of z. This is the end of part 1 of lecture 1.1. Before you proceed to part 2, you are strongly encouraged to answer the exercises included at the end of these slides. Thank you for your attention.